Okay, so in this video we'll be looking at how to design custom involute gears in Inventor, mainly for 3D printing, uh, such as the ones I have here on this drivetrain. So to design that gears, you can go to the top tab here, go to the design, and then click on spur gear. This should open a window such as this. For the most part, you don't have to worry about a lot of these things. We're just going to be looking sort of in this upper left hand corner here for the most part. Quickly, just before we get started, there's a lot of different settings here, so we'll start with what they all mean. Here you can see it says diametral pitch or module. So what diametral pitch is sort of like the imperial way of specifying tooth size, where module is sort of the metric way of specifying tooth size, and they're like inverses of each other. So high module would be a low DP, and a low DP would be a high module. For 3D printing, we want big teeth, so we'd want to increase our DP for that, and we'll get to that sort of more in depth in a second. Number of teeth is really just number of teeth, right? Center to center distance is the distance between our centers. So here it'd be like this center here to there. That's sort of important, I think, in Vex. Total unit correction, honestly, I don't know what that does. And module, again, is just how big the teeth are. So this drop down, we use it to specify how we want to generate the gears. Basically, we know what is known and what is unknown. And so we're going to select the best option for us, which we're selecting what we don't know. So I'm going to leave it here on number of teeth because I know my center to center distance and my desired gear ratio, and my I can play around with the DP to see as what works best. We could also use module and number of teeth. This option, how this differs from this one is Inventor might not be able to calculate the perfect solution to get this exact ratio with the DP that we preset. So using this option, if it's able to calculate the module and the number of teeth, it'll be able to get much closer to this desired gear ratio. Right now, if we look here to use this ratio, we'll get a 23 to 17 ratio. And if I open a calculator, 23 over 17, or 17 over 23 gives us that times 600 is about 443. So I put 450. Inventor was able to get 443 with a DP of 10, which I think is pretty good. We could also play around with this, move it to something like 13, and we'll get a 22 to 30 ratio, stuff like that. So yeah, starting here, I'm just going to use number of teeth. We're going to put in our desired gear ratio. What I've done here is I've just used a formula, which you can do in almost any dialog box in Inventor. So this is my sort of input speed, input RPM, which will be coming from these motors. So this will be 600 RPM, and what I want is 450 RPM on the wheels. So I've just done 450 over 600 for my desired gear ratio. DP, again, we can play with that after the fact, just to see how big the teeth are. I believe the ones here with 12, so I'll put in 12. Whoops. Put in 12. And then my center to center distance, you'll see I'm also using a formula here. And just to clarify what that means, oh god, it's gone. Well, we can type it in again. So I'm going to use Pythagorean theorem here because to calculate the distance from here to here. So I know that this distance here horizontally, I can actually measure this. We'll grab there and grab this here, and we can see that it's 2.25 in the x direction and 0.3245 in the y direction. So what I'll do is grab my gear gen here, and oh, it filled back in again. Let me just correct these settings back to what they were. All right, so we'll go back. So I have using Pythagorean theorem, which is just the square root of the squares, basically. So here I'll put in 2.25 squared plus I believe it was 3425 squared, just like that. I can click calculate. Everything seems good. It might show up red and give you some errors. I think if I lower this, we might, no. If it does, or maybe I can bump that up. Yeah, so it shows up red here. Honestly, you can click OK. It'll give you some warnings. You can just accept them. It's not a big deal. And then just click anywhere to place the gears. I'm just going to go back in and change our pressure angle back to 20. Recalculate it. It's all looking good. Click OK. And here are the gears. So what we've generated is a simplified view of the gears. We can see that the teeth are sort of just a normal arc there, whereas if we look at these gears, the teeth have a much more interesting shape. And again, there's no filleting down in the bottom corner there. If we need to change any of the settings, you can just right click and edit using the design accelerator. It'll bring this window back up. Not a big deal. We can also change the face width here. All that means is this distance on the gear. So like this is making a thicker or thinner gear. I'm going to use 0.2, and that's what I've used for these gears here. Calculate and OK. So now we have sort of our simplified gears here. These aren't quite ready for 3D printing, again, because it's a simplified profile of this more intricate shape. So what we're going to do is right click on it and then export tooth shape. And up here we can select either the pinion or the gear. That's either the small or big gear, whichever one you're trying to export. You don't have to worry about much here, except for the normal backlash. For that, I use usually just 0.006 inches. You can play around with this value for what works or doesn't work on your 3D printer, but I found that this works absolutely fine and haven't really encountered any problems. You can go ahead and click OK. It'll bring up a new window, and you can see here now we have one tooth that looks much different than this one. With that, now I'm just going to walk through the steps sort of how we can turn this into an actual gear. So we'll start by just extruding that tooth shape through the entire disc here, and I'm going to actually go back and grab how many teeth this generated with. So this generated with 23 to 31. So here I'm gonna, actually before I do that, I'm gonna chamfer all my edges. Maybe like a 32nd, 24th. Yeah, we'll do a 24th. And then grab our circular pattern here and pattern this all the way around our part. And I believe, no, did I say 23 times? I believe 23 is correct. I'll let it think about it for a second. I'm just gonna double check. 23 teeth, yep. Okay, so now we have a gear that has nothing on it. So let's go back here and just finish up. So I'm gonna model this gear quickly, put this little sticky out part here, and then put a shaft hole through it. So we'll come back here quickly. Just this is now just any normal part like you design in Inventor. You can do whatever you want to it effectively. Bring this out 1/16, add a chamfer to the edge there, 1/16, and now put a high strength shaft hole through the center, that all the way through, and now add one more chamfer to all these edges here. there. And so now we have a nice gear that I can now place back in. Actually, I have to save it first. We'll save this just somewhere here. I'll call this 23 tooth, just 22 tooth high strength gear. And it's important that I mentioned we shouldn't reuse these gears for different purposes because it was made specifically with one center to center distance in mind, working specifically for this. So if you were to change things around or make a different subsystem, this gear would not necessarily work. I'm gonna go ahead and grab the gear here, place it into our assembly, and we can sort of see that it's effectively identical here to the one that we've designed. So that's the first gear. Again, we can go back and do that for the second gear. This one's 31 teeth. So I'm going to right click, again, export tooth shape. This time I'm going to grab the gear, which is the bigger one, input my backlash back in here, extrude this all the way through, add my chamfer. And the chamfer is important so that, first of all, when you're printing, so that you don't have like a weird elephant's foot that is going to interfere with your gears. It also just makes them mesh nicer. And then grab those surfaces, put it around the z-axis. So is that not? Oh, I'm on a rectangular pattern, that's why. Grab both of those, put it around the z-axis. I believe, what was it, 31 times? I'm forgetting. 31. And the z-axis, 31. Now, let it think about itself. That doesn't seem right. Why doesn't that seem right? Let's just restart. Yeah, 31, export tooth shape, 6, gear, that, extrude that through, chamfer, 1/24th, circular pattern, round Z, 31, or is it 23? Did I choose the wrong gear? I did. That's why. Okay, I got it backwards. So export tooth, we're gonna just one more time. Yeah, this looks bigger, so okay. Third time's the charm. All the way through. Chamfer, 1/24th. Fly, circular pattern. Around Z, 31. Let it think. That looks much better. Disable this sketch. Then we can come back in here. And if we want, we can model what I've done here. So on the one face, I believe that's a 2-inch diameter coming out about 0.375. 0.275. Just edit that quickly. 275. We can chamfer our edges to make it look all nice. Maybe a 16th. Yeah, it looks better. And then I put a hole straight through the center. We'll oversize that by just a bit so that we can put a circle insert against the wheel. Put that all the way through. And then I'll put in these 4 holes next. So we'll go 1-inch diameter, put 4 points on it. Constrain those so they're nice and set. Grab my hole tool. We're going to countersink these by 1/8, not an 18th, an 8th. 0.375 diameter counter bore, and then 0.177 is what I use for the actual screw diameter. Click OK, and then one final chamfer. We'll go with 32nd on those two surfaces. And so now we have, oops, I won't save that. Now we have this, which is almost effectively identical to what I've designed here. And then you can go ahead, drop them back into your main assembly, and put it all together. Yeah, that's about it.